we'll introduce an important application of integer programming, TSP. We have n city to be visited, and every city need to be visited only once. So the complexity is that if you start from the origin, there are n choice. And when you go to the next city, there are n minus 1 choice. And if the rows are symmetric, that is, either direction have the same distance, then possibility is n factorial divided by 2. This kind of problem has a lot of application. For example, VRP problem. This is for e-commerce. They try to or trucking company. They try to deliver goods to their customer, or determine the drilling sequence for circuit board. And we try to find the shortest path because we try to increase throughput, which is an important KPI or matrix in modern factory. So we will introduce dynamic programming for this kind of problem and developed by 3 persons, but it's called an Held and Cobb algorithm. And Cobb is a Turing Award winner, and he's the advisor of Kamaka, the inventor of interior point. And we index the city from 0 to n minus 1, and we choose 0 arbitrarily, and starting and ending Home Depot. So we define a state. S is that is a subset of city already been visited, and origin belongs to this set. And J is the current city, and please note that J belongs to the subset S. The salesperson is standing. So the value of this dynamic programming is that this is the minimum cost. We start as city 0 and visit every city inside subset exactly once. And right now we are standing at city J. So what is the next step? So you might wondering how could we come up with this kind of state? Actually, it's a research process. You try a different possibility and finally find one that's more suitable for the problem. So we learning by imitating others' approach. So in this case, you look at different paper and try different techniques. How could you define the state? Which I'm talking about is a learnable technique. So recursive relationship. So this is the subset has been visited, and this is the final city, and it's a dynamic programming value. So we use a one step. This is the final state, right? We backward in time, and we visit I belongs to the set. And of course, I is not equal to J because every city must visit only once. So this is one step. And since we visit J, so we remove J from this set. And this is our current standing. We move from J to I, so we're standing at I. So this is one step, and this is the cost goal, which is the essence of dynamic programming. And we try to find the minimal distance. So the best case is that this is our initial Home Depot, and this is the first state, and we are standing at J. That is, we only go to one city. So that's the distance from between 0 and J. And this is our final global minima. V is the set of containing all city, and J is the final station. And we go from J to our Home Depot. One state cost to go. And you could look up the paper for the compressed analysis If we use brute force permutation, we consider all permutation is an n factorial, which is very difficult to solve. And for Held and Carp, it's a complexity n squared times 2 to the power of n, and this is spec complexity. And we'll give some numerical number to appreciate or understand the complexity. If the city number is 10, this is time operation, means time, and space means your memory. This is for brute force, time and space, and this is by dynamic programming, time and space. For small problem, you could easily solve the problem using a modern CPU within millisecond. So please know that when the city's number is small, we cannot call it NP hard. NP hard is that when you have a big problem, and for it's 20, this is the complexity for time and space, As you can see, for dynamic programming, it's roughly 1 second. By using brute force, it takes several months or years. However, when the number of cities reach 100, both fail because due to theoretical limit. So the natural question is that could we find better algorithm? This is only one algorithm, right? So in graduate school or in research, we try to find efficient algorithm. We keep improving. On the information I search, this is the fastest supercomputer right now. If you have a 100 city, even use supercomputer, it still takes several years to finish. So could we devise better algorithm? So next we'll introduce integer linear programming based on this paper in OR again. We have a decision variable x sub ij travel from I to city j with a distance or cost c sub ij. Our objective function is try to minimize, and this is the city, the number of city 1 to n, and the inner city j greater than I. That is, we choose all possible city. Why? Because we do not know in advance which one to visit. So we use decision variable to choose automatically. So this is the way of thinking. You don't know which one is the optimal. So you design a decision variable and you formulate an objective function, and this is all city, and this is from that city all possibility. And please know that, as we say, if I, for example, if 1, 2 is 1, 2, 1 could not be 1 because we only visit once. So even though there are so many turns, most of them are 0 because we only need to visit n city. So even though you have a lot of summation here, we only choose n. Most of them are 0 when you find the optimal solution. So this is constraint, it's called degree. Visit exactly once. So 1 entry, 1 exit. So the notation is that for each I is 1 to n, and j, summation over j, and we require j is not equal to I. This is the requirement of TSP. And your summation all variable should be equal to 1 entry and 1 exit. For example, x1, 3, and 3, 2. Okay, the other one is called subtool elimination. We consider every subset of city. So since this is all subset, so this is a combinatorial constraint. This kind of formulation still could not resolve NP-hard problem of TSP. It just used another problem formulation because the problem itself is very difficult. That is the main issue. So for example, if we have subtour, that is 1, 2 is one group, and 3, 4 is another group. So I find a picture to illustrate the concept of subtour. This is the correct formulation. There is no subtour, but we have 3 subtour in this problem, which is not allowed in the TSP problem. So if there's a subtour here, right? So in this case, x12 plus x sub 1 to 1 is equal to, which is not less than equal to 2 minus 1 because our subset is 2. So this kind of constraint will eliminate the possibility of the left-hand side, which is not feasible in TSP problem. And also we need integrity constraint 0 and 1. So as I mentioned earlier, the complexity comes from this every subset here. We need to consider all possibility. So this is still a big problem with many constraints, which make this kind of problem difficult to solve using pure integer linear programming problem formulation. So branch and cut, and this is a famous 4-person. They even published a book. It's called TSP Solver. And one technique is called relaxation. We see that before. Because LP is polynomial for interior point algorithm. And the other one is cutting plane. Okay, we add a plane such that this one, we try to find integers as possible solution here. So this is not feasible. So we just cut it. So this one doesn't matter to us. And also branching, branch and bound. So this kind of combine 2 methods into one is called branch and cut. And as I mentioned earlier, there are many algorithms to solve this kind of difficult integer programming problem. It might take 1 semester. This is the world record. This is a real problem. Need to be manufactured by IBM. 85,000 hosts. And total computational time is approximate 136 CPU years at that time. And they utilize parallel computing, finished in a few months. Still too slow, right? But it comes from the problem itself. It's a factorial or exponential. So it's called, one important concept is called NP-hard. Right now, no person could find polynomial time algorithm for this kind of problem. And I think most computer scientists believe that does not exist. This is polynomial. If they could find one polynomial time algorithm for NP problem, it's a big breakthrough. And also you could solve many NPR problems because many NPR problems are equivalent. That is, if you could solve one problem, you could solve the other problem by polynomial time transformation. Okay, but that conjecture has never been proved for several decades. And one foundation even offered $1 million if you could resolve this problem, prove it or disprove it. That is, it is impossible to find any polynomial time algorithm to solve NPR problem. Prove it or disprove it, and right now that does not exist. So the natural question is that we still need to go on, right? because the factory need to be manufactured every day. We cannot wait for 1 month. So operation researcher proposed many heuristic problems to find a approximate solution. As I mentioned earlier, this kind of heuristic algorithm we are taught in the other course for 1 semester again. So one famous heuristic is called LKH by 3 researchers. They solve a map. This is 1 million, almost 2 million cities with 99 perfect route, less than 1 hour. Okay, which is still amazing, right? 2 million cities. So my point is that for a difficult problem, there are many approaches to solve the same problem. When we compare, sometimes we try to trade. It's kind of trade-off, right? We try to find a suboptimal solution or approximate solution within a reasonable time. But still, it's meaningful to study this kind of important problem because when you try to attack or solve a difficult problem, you might find solution for the other problem. It is the magic of science or research.